Hi guys, in this video we're going to be looking at Gray code. So Gray code is a type of binary numbering system. So we're going to be looking at its history, why we need it, how to convert to and from Gray code, and so we'll be able to use it in applications for other parts of digital electronics, kernel maps, for example. Okay, so that's what we're going to be doing here. So why do we need Gray code? Gray code was invented in 1953 by Frank Gray from Bell Labs. Bell Labs is really cool. There's the same lab that made the transistor, C, Unix, the laser. So I think you should expect pretty cool things to be coming from Bell Labs. So let's try and see the importance of Gray code. Let's say you have something that you expect to change by only one. So I'm going to use a clock to demonstrate, but you can really picture anything else for this scenario. So 12, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and 11. So in a decimal numbering system, this changes by one. Our clock increases by one every step. But if we were to convert this to binary, okay, this would be 001, 010, 11, 100, 101, 110, 111, 10, and going on this way to complete the clock. So like I said, in decimal, 1, 2 is after 1, 3 is after 2, 4 is after 3, like so. But if we were to transmit this, let's say we wanted to send this to another system somewhere far off, that would see the value of the clock. So we would sending our bytes. So let's say we send 001 in this packet, 0010, 0011, 0100. But what if there's now interference, okay, along the lines of data transmission, and then this flips from a 1 to a 0? So let's say this affects this bit and changes it from 1 to 0. So it used to be 0011, and that would have been the decimal 3. So now it becomes 0001, which is the decimal 4, 1. So you can see, even by changing one bit, by going from a 0 to a 1, we're able to take the binary number from 3 all the way to 1. And then the kind of thing also applies if you pick another example. Let's say we wanted to transmit 7, then 2. To transmit 7, actually, the byte expression for 7. So if we had 0, 1, 1, 1, and then we randomly flipped from a 1 to a 0, and this will become 0, 0, 1, 1, and that will change all the way from 7 to 3. So you can see what happens, that usually when sending binary information over packets, you're going to expect to have errors. Okay, so the issue is that when I'm making these transmissions, how do I know that my bit hasn't been tampered with? So that's the point of Gray code, is to be able to identify that, hey, this number is after this number, this is after this. Because in Gray code, you can see that this is binary. Okay, so let's see. This would be binary 01. So this would be binary. And in Gray code, it would be no. Exactly. So this is our binary, and this is our Gray code. So we're in binary. You can see that going from 0 to 1, going from 1 to 2, this 0 changes to a 1, this one changes to a 0. So you have two bit flips going from here. But in Gray, this is the decimal 1, and this is decimal 2. Okay, but in Gray code, you can see that this stays the same, this stays the same. 0 changing to 1 is the only bit change, going from 1 to 2, and 1 stays the same. The same applies. So let's say we're going from, so this is 1, 2, 3, and 4 in decimal. Okay, so going from 3 to 4 in binary, 1 flips to 0, 1 flips to 0, 0 flips to 1. So you have a total of 3 bits changes. Okay, so if we were transmitting this across something that wasn't entirely isolated from errors, a single bit flip would really mess up our information. Okay, but in gray code, going from 3 to 4, so this is 3, this is 4, 0 stays the same, this 0 flips to a 1, 1 stays the same, and 0 stays the same. So you can see that only one bit changes when going from successive numbers, which is the very big advantage of gray code. It helps note when we have errors in transmission and improves error detection. So it's one of the important things of gray code. How it helps us to keep our transmission properly. Okay, so the XOR gates. So this is now how to define one of the binding principles behind gray code, why it works the way it does. Okay, so there are a handful of logic gates, but the most important one when dealing with gray code is what you call the exclusive OR, and it looks like this. Okay, so let's say you have two inputs, so you have A and B, and this is your output Y. I'll contrast this to the traditional OR gates. So this is what the OR gates would naturally be like. So AB, let's call this D, A, output Y. Okay, so this is OR, and this is exclusive OR. The symbol for this is irregular plus, and this is a plus enclosed in a circle. Okay, so recall from your basic digital electronics, right? A, B, and A or B. Okay, so let's say we have A, B, and Y is equal to regular old A or B. So 0, 0, 0, 1, 1, 0, 1, 1. The simple OR function would be high if either A or B, if either of our inputs is high, which means in the case where both inputs are high, it still gives you a high value. But once neither one of them is on, you're going to get 0, which is the only case you're going to get 0. But for the exclusive OR, as the name sort of hints, it is exclusively high when only either of our inputs are high. Okay, so let me use the truth table to give us the idea of what that means. So let's say we have A, B, and then Y is equal to A, X or B. Same inputs, 01, 10, 11. Then Y equals A or B will give us A, X or B, 0, 1, 1, 0. So this is the important thing about gray code. So the XOR gate is important in saying, hey, even though in traditional OR, we will still get a high value when both of them are on. For the exclusive OR, I need a high only and if and only when only one of these inputs are high. So it helps us to see that only one of the inputs are high. And this is the fundamental building block of gray code, which we'll see in the next video the next slide actually has it solved. So now how do we convert from binary to gray code? It's very simple. So let's pick a simple number. So let's do 0, 0. Let me just what's this 0, 1, 0, 0. So let's say this is binary base 2. If I wanted to convert this to gray code, the first thing to note is that the first bit is maintained. Okay, so I had 0 here. So okay, let's write binary and gray. So I had 0 here, I'll still keep my 0. So whether you're converting from binary to gray or gray to binary, one thing to note is that your first bit is always going to be the same. So this is your most significant bit, MSB. MSB stays the same. And then you're always going to have the same number of bits. Your gray can be more than your binary, and your binary can be more than your gray. Okay, so it's just one of the things that help you identify it. So we can write here to note that if it's the same, we keep it as 0. And if it's different, we keep it as 1. And remember, if we looked at our XOR table, AB and A or B, it is exactly the same thing. 0, 1, 1, 0, 1, 1. 0, 1, 1, 0. When they are the same, the output is 0. And when they're different, when both inputs are different, the output is 1. So let's see how that applies. So we are now going to check. We maintained our first bit, okay? So we're now going to check 0 XOR 1. Both of them are different, which means we keep it 1. 1 XOR 0. Both of them are different, meaning we make it a 1. And 0 XOR 0. Both of them are the same. That looks like a face. 0 XOR 0. Both of them are the same value. So that makes it a 0 in gray code. Okay, so that should be on the table. Exactly. Over here for 4. So while 4 in decimal is 0, 1, 0, 0, in gray code it's going to be 0, 1, 1, 0. Cool. So let's pick another number to see how. Let's do this. Let's do 1, 0, 1, 0 in binary. Okay, so binary 1, 0, 1, 0 base 2. I want to convert it to gray code. Remember what I said, you keep the most significant bits. So 1 in binary is going to be 1 in gray. Then you XOR them, or you check this with the former value, okay? Comparing 1 to 0, they are different, meaning my output is going to be 1. The same way, 1 XOR 0 is going to give you 1, since both inputs are different at the same time. Okay, so 1 and 0 are different, keep it at 1. 0 and 1 are different, keep it at 1. 1 and 0 are different, keep it at 1, which is 1, 1, 1, 1 in gray code. Let's do one more to get the hang of it. So let's do binary 4, 0, 0, 0, 1. Okay, let's try and make it the gray. Remember, we maintain our most significant bits, so that 0 stays. 0 to 0 is the same, make it a 0. 0 to 0 is the same, make it a 0. 0 to 1 they are different, so 0 XOR 1. 0 XOR 1 is equal to 1. It's going to give you 1, so that gives you 1 in gray code. So 1 is the same in both of them. So you can see that although the concept does look kind of difficult, understanding gray code is pretty cute. Okay, now, so we're going to try and do the same thing backwards, which means given a number in gray code, how can we work backwards to find the binary equivalent of that number? So let's see, let's work with 0, 1, 1, 0 in gray. The process is the same. It's just that instead of now you're going to be XORing with the binary number as you're forming it. Okay, so this is going to be our binary over here. To remember, we maintain the MSB, so 0 comes down. Okay, and then we work with this. So 1 XOR 0 is, recall we said if they were same, so that's XOR, we're getting a low, and if they're different, we're going to assert it and make it high. So 1 XOR 0 is, these are different, so we're going to get a high value, 1. We move over to the next. 1 XOR 1. Okay, so this kind of gives us this. 1 XOR 1. Those are the same, so we get 0. And 0 XOR 0. Those are the same, so we get 0, 2. So that's base 2. So we can come over and check, and you see that 0, 1, 0, 0. So that's 4 in binary, is 0, 1, 1, 0 in gray. So it's kind of, you move XOR, bring it down, move XOR, bring it down, move XOR, bring it down. So let's see if we can do another one. So gray of 1101, and we're trying to find the binary equivalence. Okay, so recall we maintain the MSB, so that's 1, and move over to the next. 1 XOR 1, those are the same, so we get a 0. Over to the next. 0 XOR 0, those are the same, so we get a 0. Over to the next. 1 XOR 0, those are different, so we get a 1. And you can come over and check, and you see that 1001 in binary is the same as 1101 in gray. Okay, so let's just do one more to confidently get the hang of this. So let's work with 0, 1, 0, 0. Okay. So gray, 0, 1, 0, 0. So G for gray. I'm trying to find the binary. Okay. Maintain the MSB. So that's 0. Move over to the next. 1 XOR 0, those are different. So we get a 0. 0 XOR 0, those are the same. So we get a 1. And 0 XOR 1, those are different. So we get a 1. Is that correct? 0, 0, 1, 1 base 2 or 100. Maintain the MSB. 1 XOR 0. Okay, that's the error. Okay. Let's do that again just to be sure. Okay. So 0, 1, 0, 0 in gray code. Okay, so that's 7 in decimal, so we can sort of check for ourselves. So trying to find the binary equivalent of that. Maintain the MSB. So that comes down and gives us 0. And 1 XOR 0, those are different, so we definitely get a 1. So 1 XOR 0 gave us this. Okay. 0 XOR 1, those are different, so we get a 1. And 0 XOR 100, yeah. And then 0 XOR 1, those are different, so we get a 1 too. So that's that, and we have corrected the error. So it's just to be careful, be very particular with making sure that you're doing it the right way. You maintain the MSB, take the second of the gray, XOR with the first, take the third of the gray, XOR with the second, and like so on, so you're able to convert from gray code to binary.